prove that if you take, so A and Aij, recall, are the matrix entries. So if we take this sum, gives 0. And if we consider this sum, which is the same as here, just the I is changed into an n, we get the quotient of two consecutive determinants. So Bn is the determinant of the n by n matrix. And if we manage to prove these three identities with the given C and n, that I have not yet told what it is, then the determinant evaluation follows as a consequence. Now this might look like very much metric to you, so I should give a little bit more of explanation. It's a simple trick, everybody knows, or maybe, I don't know, shall I write here? Yeah, I don't know. I try to write big that everybody can see. So if we want to compute this determinant, then everybody knows we can do a Laplace expansion. So this is nothing else. And this determinant is called Bn. This is nothing else than j from 1 to n minus 1. So we expand the last row of entries. So we get a minus 1 to the n plus j, then the minor nj times a nj, right? Now what we do is we define this c and j to be minus 1 to the n plus j m nj divided by m nn. And then we take this equation and divide it by m nn, which is the same as bn minus 1. It's just the minor with the last row and the last column deleted. So we get a bn divided by bn minus 1 equals j from 1 to n c nj times a and j. And this is the last identity on the slide. Now, what does this identity mean? Look here, the only difference is that we replace n by I. So what do we do? We are now computing the determinant of the matrix where we replace the last row by the ith row. So of course this determinant is 0, provided that I is smaller than n. So, and this is the second one. And the first one follows from the definition that for nn we get 1. So this is the background of these three identities. And then if we look at the second one, we have here n minus 1 equations for n unknowns, so we get up to multiple a unique solution. So now I will talk a little bit about the technique that I use for proving these identities. So still, we don't know about this C and N, or C and J, this unknown function that we pull out of the head. We have to wait a little bit longer until we get it. This is a little bit about the methods that I use for proving these identities. And of course, it's very unlikely that we get a nice closed form for this function C and J, because if we could get this, then it would, we would also get a nice closed form for the determinant itself, because the C and J, it's just like it's a combination of these minors. So it's very unlikely that we can get this, but we can get a implicit description in terms of recurrences, and these are called holonomic systems. And I want to give you a very simple example just to give you an idea. We consider the binomial coefficient n choose k, and as you know, you can express or you can define the binomial coefficient with these two recurrences. One goes in n direction and the other in k direction, and you need one initial value. And then by these two recurrences, you can go to any point you like and compute the value of the binomial coefficient. So these two equations form a holonomic system that define the binomial coefficient. For the Q binomial coefficient, this thing looks very, very similar. Just replace every k by q to the k, and so on, and do some cancellation, and you end up with a similar set of recurrences. But observe that now, instead of the coefficients, here were polynomials in n and k, whereas here we have polynomials in q to the k and q to the n, and also q. Like here we have q times q to the n, and then times q to the k. So we have one variable more than here. This makes it more difficult. And in general, we don't need that these recurrences are of order 1. They can be of higher order. They can be more than just 2 recurrences. So these in general are called holonomic systems. And we can do this recurrence calculus. So if we have these two recurrences, we can combine them in some way. So what I do here, I took the first one and shifted it by k. I replaced k by k plus 1. And the second one also, I replaced n by n plus 1. I get this recurrence, which is also a valid recurrence for the binomial coefficients. Then I can add them up. So I can do this calculus on recurrences, shifting and adding and multiplying by some constant. And all these operations, if I translate the recurrences into an operator algebra, so I introduce an operator that represents the shift with k or with n, then I get a non-commutative operator algebra in which these operations just correspond to multiplication and addition. So I have translated the recurrences into a kind of polynomial ring, non-commutative polynomial ring, in which I can more easily calculate. And then the set of all valid recurrences for this binomial coefficient in this case forms an ideal in this non-commutative polynomial ring. And for ideals, I have to mention a little bit of background to also promote the place where I'm coming from. So if we speak about ideals, the question is always the ideal membership problem. We want to know whether a given recurrence is in the ideal, or in other words, is a valid recurrence for the function in question. And so we have to decide whether it's a member in the ideal, and this can be solved by what is called Gröbner basis. This is one tool for deciding this problem. So, and this is what I will use. So I will compute Gröbner basis of these ideals that I will use. And so my personal connection to the Gröbner basis is that they have been invented by Bruno Buchberger, who is the founder of RISC, where I got my PhD from. So now I tell you how we obtain this yet unknown function C and J is here, mainly by guessing. So we assume that it allows a description via holonomic systems. So we guess recurrences by ansatz. We make an ansatz, we fix an order of the recurrence and the degree of the coefficients. We make an ansatz with unknown coefficients and then plug in some values that we know for the unknown function. And our expert at RISC is this guy, Manuel Kauers. He has written a very powerful software that can do such guessing. And this provided a bunch of recurrences for this unknown function C and J. So here I sketched these recurrences, but to make them fit onto the screen, I left away all the coefficients. So for each term you have to imagine that there's a coefficient which is a polynomial in n and j, or in the q case in q to the j, q to the n, and q. So if we want to look at these recurrences in full, so I have loaded it here into my program, and I show you the smallest of those. Okay, here it is. So, well, you see, this is And I think we have now seen like 5% of